Hi engineering students, this is the video for week 3A, and just want to start by saying good job everyone on getting the first assignment in. It was due on Friday. I guess Google Classroom makes it due at midnight and you all got it in, so that's fantastic. And I'm always going to wait till the end of the week before I even think about grading them. I want to get them all in hand at once. So even those who submitted it like on Tuesday, and there were a few of you, don't expect any feedback till the next week. And I will give the feedback directly through Google Classroom. And I won't necessarily give you feedback on every last thing, because that would be a little too much. But if you want to book a time with me to go through it, I will absolutely do that. And that's way more profitable than me writing down a whole bunch of comments that you may not even read. So I'll give some feedback, but please take me up on that. We can do a little Zoom meeting anytime you want and go through it. Okay, so I'm going to do a quick refresher on last week to begin with. I want to ask you for this triangle. Here we go. Oh, great. Thank you. Cleaning that up. If you have a triangle that has a hypotenuse of 200, and let's not even do units. Let's say this is a purely mathematical triangle. 200, and we'll do an angle of 40 degrees. I want you to pause the video and see if you can solve this triangle. And remember, to solve a triangle means to find all of the missing sides and angles. Okay. All right, hopefully you paused and you attempted that. So first up, it's really easy to find the missing side. The missing side is going to be 50 degrees because we know that the sum of all the angles is going to be 180. And that's me again using the sigma notation, and I'm using it in the kind of general loose sense. Sum of angles is 180 degrees. Now, to find the other two sides, we need to start by picking a reference angle. And let's just use the first one. Let's use that 40 degrees. And once you do that, then you can label this side as the adjacent side, this side as the opposite side. This side was always the hypotenuse, that doesn't change. And then you're going to want to use those sine, cosine, and tangent functions. And you do need a calculator to do this. Okay, so remember that sine of any angle, theta, is the ratio of the opposite side to the adjacent side. Okay. Oh, I am so sorry. Sorry about that. That should have said hypotenuse. Okay, so that is the SOH. All right, here it is, SOH in SOHCAHTOA. Again, I know that some of you know this backwards and some of you are just hearing it for the first time. So I'm trying to pitch it to kind of the 9th, 10th grade level right now. So you write that equation just like I have right there, and then you fill in the things that you know. So you picked 40 degrees as your reference angle, so you put that in. Now, this is where you pick up the calculator. So I've got mine on the side, you can't see it, but I do have it. And I type in sine of 40 degrees. And what I get, hold on, I get 0.6428. And that is to 4 significant figures. So what this tells me, remember, is that the opposite side, because the sine function deals with the opposite side, the opposite side is going to be 64%, or 0.6428 of the hypotenuse, because this is a ratio of sides. So, you know, what is 0.6428 times that 200? So I still have my calculator, I still have that number on the screen, so I just do times 200, and I get 128.6. All right, so that must be the length. I'm going to fill it in over here, 128.6. And I can use the cosine function. Cosine theta equals adjacent over hypotenuse. Okay, that is the CAH, SOHCAHTOA. And when I do cosine of 40 degrees, I get a different number entirely. I get 0.7660. And that is saying that it's going to be 77% of the length of the hypotenuse. So we, excuse me for a second, we apply that to that number 200. Let's see, 0.7660 times 200, and I've got that on my screen still, so all I have to do on my calculator is tap out times 200, and I get 153.2. Okay, right there, 153.2. So I've just solved the triangle. I found the two missing sides, I found the missing angle, and all is well. Okay, I think that's all we need for now. Now, again, that was more work than actually what was on the assignment for the 9th and 10th graders. So I'm trying to ease into it gently. I'm still trying to teach it, but I'm not actually assessing you on that yet. But it's definitely going to be more and more coming up as we get along. This will be done just by instinct before too long at all. And then when you hit this in geometry or algebra 2, you are going to excel. You're going to be so far ahead of your classmates, and that's awesome. Now, a little bit of clarification on significant figures. Okay, because I checked in with Mr. Hurt over the past week, and I need to actually go back and correct something that I said. So here we go. And some of you might have noticed actually that when I wrote 200, but then I gave my answers as 128.6 and 153.2. In other words, I gave an answer with 4 significant figures, but how many did I have in that original 200? Well, that's kind of a funny question, actually. How many significant figures is that? I asked Mr. Hurt this and said, hey, this is really annoying to me, and I'm actually going to start a new screen here. I said, this is really annoying. Like when you have something like, okay, I said like, you have like 8,000 pounds. How many significant figures is that? Well, it seems like it should be 4, right? Oh, wait, I'm sorry. Sorry about that. Seems like it should be 1. That's what I said last week. Because you had the 8 and then those trailing zeros don't make any difference. But I said, well, hold on. What if suddenly the force adjusts? Maybe it increases to like 8,001. Do you now have 4 significant figures because you happen to be like 1 pound more than you were? That doesn't seem fair. That doesn't seem correct. And he said, yeah, the answer is that when you give a number like 8,000 pounds or even 8,001 pounds, but more so like 8,000 pounds, it is actually ambiguous. You haven't really clearly said how many significant figures that you mean. It could be only 1, but it could also be 2, it could be 3, it could also be 4, and you just really haven't said it clearly. Maybe you do actually mean exactly 8,000, okay, like to 4 significant figures. He said the only way to show it absolutely unambiguously is with scientific notation. So if I say 8.000 times 10 to the 3 pounds, that seems like a far more complicated way to write it, and I guess it is. But now we have absolutely clarified. This is 4 significant figures, and there is no doubt about it. All right, so that is the answer. So, using scientific notation is the way that you guarantee how many significant figures that you have. Okay. All right, so we're going to go from here and get into the actual lesson for today. That was all just a review and a little bit of clarification. we are going to show, yes, I keep closing the door. If you can hear those noises in the background, I keep closing the door as people try to come in. Ever experienced that? We're going to talk about vectors and scalars. And you're going to find this lesson is a little lighter than than the ones for the last week. I know it was a pretty quick pace. And as I said in my Google Classroom announcement, please don't give up. It does get better. It does get easier. This is training, and training always hurts. Training involves time, it involves effort, and it doesn't just come naturally. But if you want to get to the fullest, coolest stuff, then you have to walk through these little trials. And that's just what it is. So today, a little simpler, vectors and scalars. So everything that we can measure is one of these. Okay, if you've ever measured something, it was either a vector or a scalar. And the book mentioned this. I'm hoping you're reading the book first and then you're watching the video. That's the best way to do this. The big difference is that a scalar has no direction attached to it. And not only does it not have direction, but like it just couldn't even possibly have direction. Like it wouldn't make any sense to attach a direction to it. So when we talk about scalars, we're talking about things like temperature. Okay. Here's a little test for you. What was temperature measured in the SI units? It was capital K for Kelvin. Also, obviously, in the metric system, we use degrees Celsius. In the US customary, we use degrees Fahrenheit. There is another one, by the way, but you don't need to know it. I'm not even going to tell you. How about that? Something like time. Time is actually kind of nice. Time is only ever measured in seconds in any of our unit systems. That's consistent. Time can't have a direction associated with it. Temperature can't have a direction. You can't say that something is 900 degrees Kelvin up or to the left or down. Okay, you can't give it a direction. Some other quick ones would be speed, which we measure in meters per second or feet per second. Mass, we measure mass in kilograms, and technically we measure mass in slugs in the US customary. More on that later. Energy is another one. Energy is measured in joules in the metric system and measured in calories in the US customary system. Now, none of these have direction, okay? You might be wondering about a couple of these. You might wonder about like speed or energy. Can't things have kinetic energy as they move? Like, wouldn't that imply direction? The answer actually is no. And there are some good reasons why that is. What about speed? Like, don't you run in a particular direction? Don't you drive with a certain speed in a certain direction? And the answer is no. When we use the word speed in physics, we're talking about just your like rate of travel, like 100 miles per hour, 25 meters per second, whatever it is, but without the direction information attached. Like, that's what the word speed actually means. So watch out for that one. When you don't attach a direction to how fast you're going, it is called speed. All right, now in the vector world, these are ones where you really have to attach direction. Okay, it doesn't make sense if you don't. Like, you don't have the full picture if you don't have the direction. So these are things like force. Force is measured in newtons in the metric system, or pounds in the US customary. We've been talking about force already. We have displacement. Displacement is kind of like distance, but it's the vector version of distance. It's when you say, like, I went 300 meters north, okay, where you actually give the direction. We call that displacement. I went 200 feet down. All right. Uh, Another one would be velocity. So velocity is what we call speed. Yeah, I'll start this one as well. When we have the speed, but we also give the direction, now we call that velocity. So it still is measured in meters per second or feet per second, but you also say 300 meters per second east or whatever it is. Another one, which is a little weird, but I'll mention it here, is moments, which are measured in either Newton meters or foot pounds is probably the most common. Moments do have direction, but they have like a rotational direction, so it gets a little more complex. If you want to get into how moments work as vectors, if you want like an extra extension, then just read page 47. I recommend this really only for the 11th and 12th graders, but it'll show you how there's a special type of vector we can draw. It's called a double-headed vector. You'd actually draw it with two heads, okay, double-headed monster, and it has a particular rotational aspect associated with it, and it's more complex, more different. It has to happen in 3 dimensions. You can't really do it in 2 dimensions, and if you want to read about it, you can. That's all I'll say about moment vectors for now. We will use moments, but we won't use them as vectors in this course. Okay, so focusing on vectors. That's a list of some common vectors and scalars, but we really want to talk about the vectors more. So when it comes to a vector, once again, you have both direction and magnitude. And if you've watched Despicable Me, you know all about that. Our book, instead of the word direction, it uses the word sense. It means the same thing, okay? Sense, direction, like what's the sense of the vector? What's the direction of the vector? Those are synonymous in engineering. We're just saying, is it up, is it down, left, right, 30 degrees that way, whatever it is. Even positive and negative can be used in that way. Another one which our book mentions is the point of application. Now, I've never actually included this in my list of what defines a vector, but I think it's helpful. So I'm going to run with what the book is saying. The point of application is like, where is it being applied to? And not all vectors really kind of work in this way, but I guess, ultimately a force or something is usually sort of felt as being happening somewhere. Maybe something more like a velocity doesn't really have a point of application. It's not like the velocity is being applied, it's just happening. So that's why maybe I've never bothered mentioning that before, but I'll include it here. Okay, so let me give you some easy examples here to begin with. All right, here's me. It's only a little harder to draw, but not very much on this computer screen. So here's me, and I have a weight. I'll use capital W. Capital W is a very acceptable, very common symbol for weight. I have a weight of 155 pounds in the US customary system. So let me quickly check in with you. Why is weight a vector and not a scalar? Why do we call it that? Does it actually have a direction? Okay, remember this is the thing which sets apart vectors from scalars. You have to be able to assign a direction to it. So why does weight have a direction? Well, because it is actually a force. Weight is a force. This is not your mass. This is not the inherent property of like how much atomic stuff. This is a force, and it's the force of gravity. Okay? And the force of gravity is what we call weight. Like that is the same thing as weight. Triple equal sign, by the way, means equal and equivalent in all situations. That's some logic language for you. And it always does have a direction, and that direction is towards the center of the Earth. For everyday purposes. We could argue about that, but that's the basic meaning for what you need to know. it's a force, it has a direction, it has a magnitude. Magnitude in this case is 155, and the direction is straight down. So here's how I would show that. I'm going to draw the point of application. It looks like my belly button because that is about where a human's center of gravity is. Center of gravity is something we'll deal with later, but it basically just means, like what's the balancing point? If I were a thing and I was going to balance on the, tip of a fulcrum, or if I was going to hang from a certain point and stay balanced, that's my CG, my center of gravity. And we often use C.G to represent center of gravity. Does not mean centigrams. In this case, it means center of gravity. And I draw the arrow straight down, and there it is. We have a few things here that the book mentions. Let me switch colors. So, like we said, we have the point of application. You can draw that with just a little tiny dot if you need to show that. This is also called the tail of the vector. This part here is called the shaft, and this part here is called the head. Exactly like an actual arrow has, like the arrow that you fire in an archery lesson. You got a tail, shaft, and a head. And the one thing I haven't shown yet is the label. Okay, and this label is going to be right here, 155 pounds. Please don't leave off the units if it has units. And the only time it won't is if it's like a purely mathematical situation. Yeah, I think that makes sense. You draw your drawing, you show your vector, and we leave it at that. Let me give you another one. Oh dear, I actually wanted to keep all that. There we go. Let's say I'm standing there and now suddenly the wind starts blowing, and it's blowing to the side, and wind is not as strong as my weight force, so maybe it's like about 20 pounds. And I'm going to say that it is applied roughly right here. Okay. There you go. The force of the wind is 20 pounds. It's blowing exactly sideways. And what else is there? I've got a tail, I've got a shaft, I've got a head, I've got the label, I've got the point of application. I'm just showing what's happening. Now, in general, I have a little saying, and it's this: length is proportional to strength. Now, in the book, the author actually says kind of the opposite. He says, like, he does not recommend that you try to make the length of the arrows proportional to their strength. Now, you know what proportional means, right? That if you want to show something that is twice as strong as something else, like twice as much force, that you would show the length of the arrow as being twice as long. If you can do it, you should do it. If you can show your arrows as being in correct proportion to each other, you should, because then there are other things that you can do later on which will get easier. But sometimes it doesn't make a lot of sense. Like if I were to actually show that 20-pound vector proportional to the one which I started with, the 155-pound vector, the 20-pound one would be really small, like so small as to be almost annoyingly small and not very usable. So I actually made it a little bigger than it would have been if I had been drawing to scale. And we all know what it means. You should at least show it as, like, try to show it as being smaller. But yeah, if I were to draw it to actual scale, then it would have been like, like that kind of size, and just a little too small to be practical. But yeah, that's my rule of thumb. Try to do it, but it doesn't always work out, and that's okay. All right, now we'll go to a new page. What about when you have vectors that are not purely horizontal or vertical? For example, let's say that I am pulling with my cartoon hand on a cart, like a cart, sorry, like the kind that you might take to the beach, say pull your children around with, something like that. You're pulling on a cart, and unlike the wind or the gravity force, the weight force that I showed already, the weight force was straight vertical, the wind force was straight horizontal, but most forces are not. And so you can show them, let's see, you can show them something like this. I'm going to pull on the cart, and I'll show what the cart is experiencing for those who know what I'm talking about when I say that. The cart is experiencing my pulling force, and we have to label it. Maybe it's 35 pounds. But we need to show just what the direction is, because remember, every vector has two critical bits of information, the magnitude and the direction. Magnitude's no problem, it's the 35 pounds, but what is the direction? The other ones were obvious. They were straight vertical, straight horizontal. That was all I needed to show. That was implied, but right now, like, what is the direction of this force that the cart is experiencing? Well, what we have to do is show something called a reference line. And in general, you should make those horizontal or vertical. There are other situations where, like, maybe you're pulling something up an inclined plane, and maybe it makes more sense to use the inclined plane as the reference angle. But usually it's just horizontal and vertical. So you draw a little reference line with like a little dashed line like you see there. And then you need to show what that angle is. 45 degrees. All right. That's a very, very standard way to show it. Actually, maybe let me use a slightly different angle. Let's say that it's 50 degrees. Now, it would have also been correct. I could have had the option. Maybe I could have showed that vector again. Okay, still 35 pounds. But I could have also chosen to use a vertical reference line. And if I had done that, the angle that would have been right here would have been, drum roll, 40 degrees, okay? That's the complement of the 50, okay? Complement is when the two angles add up to 90 degrees. So either one is correct, just keep track of which one it is, make sure your diagram is labeled clearly. Both of these diagrams I've drawn are perfectly 100% acceptable. They have the reference line, it can be vertical or horizontal. They've got the angle, they would both be correct. They are two complementary angles. They express the exact same thing. Okay, now here's one for you. In your notebook, I would like you to do this. Draw an elephant. Yes, an elephant. Make it as ridiculous as you want. Just don't spend too much time on it. And I want you to show an elephant with a weight of 60 kilonewtons. You should probably pause the video, do that, because I am about to go for it. Here I go. My elephant. These are the tasks. As it is. By the way, 60 kilonewtons is absolutely about what an African elephant weighs. I know because I looked it up. African elephants are the largest elephants. There's Indian, there are Sumatran elephants, there's all sorts of elephants, a little bit of shading maybe. Elephant CG, probably somewhere around here. Draw it straight vertically, 60 kilonewtons. Oh, and I don't know if you've forgotten, but you should know this. That means 60,000 newtons. If you wanted to do it in scientific notation, depending on how many significant figures you wanted, that would be done like that. 6.0 times 10 to the 4, that now is explicitly saying 2 significant figures. All right, so that is what you should have. I'm actually quite pleased with that elephant. All right, here's another little quick exercise for you. Show me a plane flying north, and I want its velocity, its northern velocity, to be 120 meters per second. And I also want you to show an acceleration vector. Okay, accelerations result when there are unbalanced forces. They slow us down, they speed us up, they change our direction. I want an acceleration, lowercase a, of 20 meters per second squared to the southeast on your diagram. Now, you don't have to know everything that acceleration means. You don't have to know what it would do, what would result. You don't have to know the mass of the aircraft or anything like that. I just want you to show those arrows in those particular directions, looking top down at an aircraft. So pause the video, see what you can do, because here I go. I'm going to do a nice delta-winged fighter jet. Oh boy, don't do that to me. It really wants to clean up my drawings, which, you know, I won't take that too personally. Here we go. We need some missiles and things. Maybe some like flaps and ailerons and stuff. There we go. Now we'll show our vectors. The plane is flying north at 120 meters per second. Oh, you know what? Look, let me help you guys out. Let's do a little compass. We've got north, east, south, west. In Australia, here is what we were told as children: never eat soggy wheat bix. If you want to know what wheat bix are, they were kind of like a brownish, well, they were brown. Don't do that to me. They were a brown brick of like compressed wheat cereal. I kid you not. A brown compressed little brick, like maybe about like, 4 or 5 inches long, and you would get like 3 of them typically, like arrange 3 of them in a bowl, and then fill the bowl with milk and sprinkle some brown sugar on it, and they kind of soak up the milk and fall apart. Looking back on it now, that seems like the weirdest thing ever. And so the rule in Australia is you never eat soggy Weet Bix. That's how we remember. Yeah, sorry for that little aside, but I thought that might have been good for you to hear. Alright, so let's show these vectors. 120 meters per second north. You can show that like that. 120 m per s. Plane's flying north. We've got a top-down view, so we just draw it straight up. Now, the southeast, 20 meters per second squared. I'm going to show that right here like that. Now, this is not in proportion. It is not exactly 1/6 of the length of the 120. Okay, 20 is 1/6 of 120. But I didn't draw the length of it as being exactly 1/6, but it's definitely shorter. You can definitely tell. And what I also really want to show is a little reference line and then a little angle measurement. Okay, so that is clear exactly where that thing is. And by the way, this is okay. You might think this is weird that a plane is flying forward but accelerating backwards and to the right. That's perfectly fine. That just means that he will be slowing down. He will be accelerating to the right. Both those things can happen at the same time. If he keeps doing that, he will stall and fall out of the sky, but that hasn't happened yet, so it is still okay. Good. I hope you did okay with that. I hope if you didn't, that that it's making sense, that it's getting there. Now, here's a few other things that I will mention in regard to vectors, kind of like some loose bits and pieces. The book mentioned that when you are writing vectors in like print, like in an actual book, there's some different ways that we do that. So you might be reading the book and it'll say what, this is in a book, you're reading this, what is the magnitude of the vector A? Okay, so a few little conventions to be aware of. Firstly, vectors are almost always written with capital letters. Okay, it's just what we do. In print, not in handwriting, but in print, they are usually written in boldface type. I'll kind of bold it out for you, like that. Okay, bold. That's not clear. Now, with handwriting, we don't really use bold when we do handwriting, so that doesn't work. So another way to do it is to show with a little vector symbol above. So when writing things, you put a little tiny vector like that. It's a little vector, it points to the right. It's a very, very well understood symbol, and you will also see that in print as well. There are some other ones as well. You can have the little tilde is another one that I've used a lot over the years. Sometimes, I'm going to say, no, I was going to say something else, but I think that's wrong. So, yeah, but probably the little arrow, this is the best one for you to use in your handwritten work. So that is the one I recommend. And another thing that we show as well that will often come up is the magnitude of the vector, like how strong it is, but stripped of all directional information. We show that with absolute value symbols. Like, you know how you show like -3 and then you put the absolute value symbols and that equals 3. You've been using that for a few years now, all of you. We can also do like, what is the magnitude of vector A? And then, the answer might be 200 newtons. Okay, notice now you've stripped the directional information, and it's actually the exact same process for both of these things. The -3 being stripped down to a 3. Think of a number line. When you are on a number line, you start at 0 and you go, here's like your -3, and you go, all right, 1, 2, 3, and you went to the right. Okay, so when you take an absolute value symbol and you strip off the negative, so everything sort of just becomes 3. -3, +3. It's saying, I don't care if you're moving to the left or to the right, I just want the amount of distance that you moved. And that is 3. I don't want direction, because positivity and negativity are actually directions. So you've actually been using vectors your whole life. But I just want the 3. So the same way here, if you're like, what's the magnitude of direction A? That's what I'm doing right here. You say it's 200 newtons or feet per second or whatever. Okay, I don't care which direction, I just care how much. So you'll see that a lot. All right, one more thing about ways that we can show this, particularly in print and in equations and things. You might sort of skip a diagram. Let's say you've got, I don't know, you got a little, again, like a, wow, that's could be my worst car that I've ever drawn in my life. All right, we're going to leave that exactly as it is. This car might be experiencing a lot of forces. It might be experiencing like a force of friction. That's low. That's subscript FR right there. From the road, it might be experiencing, I don't know, capital D, a drag force, and then it might be experiencing, I don't know, maybe there's another car towing it as well in front. I don't know, capital T. So you can show, like, as long as those forces are all like horizontal, they're all lined up the same way, you can show that in an equation by doing something like this. You can say, all right, sum of all forces, there's sigma again, and then you give a little sketch on the side that defines the positive direction. Sorry. Okay, we're trying to define the positive direction. We do that with this little symbol on the side, okay? A little arrow that's clearly horizontal to the right with a positive symbol. And you can define whatever direction you want, by the way. It could be up, down, left, right. You say equals, and then you'll start to list off what you've got there. Let's see, we would have the drag force, D, which is now defined as being positive. Here, maybe I should show those vector symbols. It's now defined as being positive because it was lining up with that direction. You see that? Because it's in the same direction as that positive symbol there. It counts in the equation as a positive force. And you keep going. So, all right, we also have a positive force of friction, again, because that direction is the same as that direction. And then we have one last force. We have the tension or the towing force. And we're going to actually subtract that one because it is in the opposite sense, the opposite direction than what we defined as positive. Okay, so you will see this kind of notation a whole lot this year. This is how we simply show it, like in an inline equation, and we kind of got lucky with this one because everything was horizontal. And when things aren't all horizontal, you'll see later on what we do about that. Some of you already know. Okay, the last thing that we'll finish off this video with today, we'll give a little bit of a preview of what next week's reading is going to be about. Next week's reading is going to have a lot more math in it than today. And so I want to like kind of front load some of that to relieve some of the mental pressure. So the basic idea for next week, we're going to start by also pointing out that we can represent vectors by using the Cartesian plane. Okay, Cartesian plane. If you can't read my writing, that's C-A-R-T-E-S-I-A-N. Cartesian plane is named after René Descartes, the French mathematician and philosopher. Mr. Rotman might have talked about René Descartes in his classes because he had a lot to say about philosophy. The Cartesian, that's coming from René Descartes, his last name. I don't know why it's not called the Descartesian plane, it's called the Cartesian plane. Maybe de is kind of like, I don't know, just like a prefix that doesn't count in French. So the Cartesian plane is the thing that you've always known about. It's the XY plane, okay? In 2 dimensions at least. It's the XY plane, so let's draw something like that right here. And here's the, whoa, I'm going to try that one again. It's almost better. Okay, this is the Cartesian plane. Okay, just a new name for something you've always known about. Because René Descartes was the first one to put geometry into an XY coordinate plane. Great job, René Descartes. By the way, in French, René is not a girl's name. it's a guy's name, in case you're wondering. Now, let's say a person starts at, like a person is wandering around, and they start at the origin, 0, 0. And a person starts walking, and maybe this is like we're looking at a map or something like that. And they wander around, they get a little lost, they and they end up, I don't know, right here. Okay, kind of like a treasure hunt. What are those coordinates? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5. Okay. Okay, just simple XY coordinates. And this also applies in 3 dimensions. You can have an XYZ coordinate plane that is shown to you in the book. I don't really plan on using 3 dimensions in this course. It's a little more than what we want, but you are going to see it mentioned. So just don't freak out. We're going to focus on the 2 dimensions. So in a Cartesian plane, because you've got all these coordinates so neatly defined already, it just makes it really simple to then draw the vector that is associated with that. Let me try this. That was pretty good. Okay, so here is a vector. Oh, except I want to, no, that's fine, that's fine. This is what we call a displacement vector. Okay, displacement. Displacement is the vector version of distance. Okay, the distance is what I drew in the blue with the dotted line. The displacement is what I drew in the purple with the arrow. Distance is a scalar. Displacement is a vector. Okay, distance is where we say this guy walked 300 yards in all of his wanderings, but his displacement vector is going to be less magnitude than that. The displacement vector only cares about the start and the end. It doesn't care about the path. Displacement is what we call path independent. Fancy word for you. If you don't know what I'm saying, what that means, that's too much, don't worry about it. Just trying to give you some extra bits. But this displacement vector is now right there for us. We aided in the drawing of it by using the Cartesian plane. So this is coming up in the second reading this week. And as I say, I just wanted to front load that a little bit. And we could also use the Pythagorean theorem to work out. Yeah, we should label this thing at some point, huh? Let's label this with D. Okay, lowercase d. I'm not going to draw the arrow over it because it's pretty obvious. The arrow is right there. The actual vector arrow is right there. And we could work out what the absolute value is of that vector. Like, what is the length of that vector? We could do that by using the Pythagorean theorem. Okay. You know that a squared plus b squared equals c squared. We already talked about that. So a little rearranging of the Pythagorean theorem. You take the square root of both sides, and that tells you what that hypotenuse length is. The hypotenuse, the absolute value, the label, these are all the same thing. They're all one and the same when talking about vectors. So if I want to know what is the absolute value of this particular displacement vector, it's going to be the square root of 8 squared plus 5 squared. Okay, the like horizontalness of the vector and the verticalness of the vector, we run those through the Pythagorean theorem, and that gives us the length of it. Let me do that right now in my calculator on the side. You may have already beaten me there. I don't like the calculator I have, but I'm working with it. In fact, I can't even find the things that I want. Hold on. All right, 9.4, let's say. 9.4. We didn't give any units anywhere, by the way, so I won't report back units. If you weren't given them, you don't need to report them. But the absolute value of this vector, the length of this vector, the label of this vector is 9.4. Okay, so that covers the first couple of pages of the reading next week. You've been prepared for it. We're a little bit early in our lesson length today, so that's great. So keep on with those discussion board comments. They're great. Do check back. See if this week, see if you can answer somebody else's comment before I do. See if you can beat me to it. That also counts as your discussion board contribution. If you do that, you don't need to ask your own question. You can just speak to someone else's. All right, that's it. We'll see you in another couple of days. Thanks, everybody. Bye.